Greetings, my name is Samuel, and in this video I will aim to provide a digest of Contrastive Language Image Pre-training, or CLIP as it is better known. This method was introduced in the paper Learning Transferable Visual Models from Natural Language Supervision by Radford and co-authors, published at ICML 2021. Here is an outline of what will be discussed. We will start out with motivation. We will then discuss the data and method underpinning CLIP, and a range of experiments that were conducted to assess its abilities. Next, we'll discuss the data overlap analysis performed by the authors to check for data contamination in their pre-training, as well as limitations, broader impacts, and related work. Finally, we'll conclude with a brief summary. Let's begin with the motivation. The first observation made by the authors is that traditional computer vision systems are typically trained with a fixed set of predetermined object categories, often on annotated datasets such as ImageNet. While this approach has had many successes, it limits flexibility, since each time we encounter a new visual concept, we need to retrain the model with labeled examples of this concept. This poses the question of whether we can train a vision model such that it works in a zero-shot manner without requiring fine-tuning for new classes. A second observation is that a number of prior works have shown that learning visual representations from natural language descriptions, rather than fixed labels, can be extremely data efficient. Two notable examples of such prior work include Vertex, which showed that by training a model for the task of image captioning, it could transfer to downstream tasks in a manner that was highly data efficient, using many fewer images than is required with classification pre-training. The Convert framework of Zhang et al. Illustrated that by encoding images and natural language descriptions independently, then training the encoders to match paired data with a contrastive loss, visual representations could be learned with a small number of examples, in this case in the medical image domain. In light of this, it is natural to ask, can we leverage the data-efficient supervision of natural language to efficiently train our zero-shot model? A third observation is that natural language processing systems have benefited tremendously from scale. Systems like T5 and GPT-3 have shown that with large-scale training, zero-shot transfer becomes practical, illustrating that noisy web-scale supervision seems to surpass manual curation for NLP datasets. To scale up image training, one option would be to scale up manual annotation of images, but this would be prohibitively costly. However, thanks to alternative text or alt text descriptions in HTML, there are large quantities of images with text descriptions online. Given this, it's reasonable to ask, can we scale up vision training by using web text rather than manual category labels? With the motivation in place, we can move on to the data and method behind CLIP. We turn now to the building blocks of the approach. We'd like to explore the benefits of large-scale natural language supervision, but prior work has sought to learn visual representations from natural language using datasets of limited scale. In particular, the datasets employed have been MS-COCO and Visual Genome, both of which contain on the order of 100,000 images, and YFC 100 million, which contains 100 million images, but many of these are associated with noisy metadata. After filtering to images with usable natural language descriptions, the dataset is reduced in size to 15 million images. By contrast, strong vision classifier systems have benefited from training on datasets exceeding 3 billion images. Given this disparity, to assess whether natural language supervision can work efficiently at scale, a new dataset is collected. This dataset is built by searching for image-text pairs with a set of 500,000 queries. The search queries for the dataset are formed from words occurring at least 100 times in English Wikipedia, which are then augmented with bigrams exhibiting high mutual information with these words. Other queries are formed from names of Wikipedia articles above a given search volume threshold, and any synsets of WordNet that were not included by the steps above. A form of approximate class balancing is performed by including up to at most 20,000 image text pairs per query. The resulting web image text, or WIT, dataset contains a total of approximately 400 million image text pairs. A second consideration relates to the choice of pre-training method. It's worth noting here that the strongest computer vision systems employ significant amounts of computation for training. For example, the 2018 Instagram model of Mahajan et al. Used 19 years of GPU time, while the noisy student model of Xie et al. Used 33 years of TPU time. When it comes to selecting a pre-training method suitable for natural language pre-training, efficiency is a key consideration. The initial approach explored by the authors of this work was a captioning model inspired by Vertex. Here we are plotting number of images processed on the x-axis and zero-shot ImageNet accuracy on the y-axis. The initial baseline did not appear to scale very efficiently with additional training data. A simplification of this method, bag of words prediction, was 3 times more efficient. Noting that these methods may be limited by their requirement to predict the text exactly, the authors then experimented with a contrastive method based on whole image text matching, on the assumption that it may potentially provide an easier proxy task. It is from here that the name CLIP derives as an abbreviation for contrastive language image pre-training. They found that CLIP brought a further factor of 4 improvement in efficiency over the bag of words baseline. Rather than predicting words directly, CLIP works by ingesting n image text pairs and is trained to predict which of the n by n possible pairings is valid. We can now dig a little deeper into how this contrastive pre-training is performed. CLIP is optimized by training image and text encoders that maximize the cosine similarities between the n valid pairings of images and text within each mini-batch, and minimizing the cosine similarities of the remaining n squared minus n invalid pairings. How this works in practice can be understood with the help of some pseudocode provided by the authors. We assume that we have as inputs an image encoder, in this case either a ResNet or a vision transformer, as well as a text encoder, which could be a continuous bag of words model or a text transformer. The input to the image encoder is a mini batch of aligned images, with batch elements along the first dimension and height, width, and channels along the remaining dimensions, while the input to the text model is a mini batch of aligned text, again with batch elements on the first dimension and padded to some fixed length on the second dimension. In addition to the base encoders, the model also uses a matrix WI that learns to project image embeddings to a dimension of DE, and a matrix WT that is learned to project text embeddings to the same dimension, DE. Finally, the model includes a learned temperature parameter, T, for scaling purposes. To compute the CLIP loss, we first extract features for each modality by passing the images into the image encoder and text sequences into the text encoder. Next, we compute multimodal embeddings in the shared DE dimensional space by projecting the image features by WI and L2 normalizing, then projecting the text features by WT and L2 normalizing. We use these embeddings to compute an n by n matrix of scaled pairwise cosine similarities via a matrix multiply and multiplication by the exponentiated temperature parameter. Finally, we compute the loss value by generating n labels and penalizing logits that fail to assign all their mass to the diagonal of the matrix along the image dimension and along the text dimension, before averaging the result to produce the loss. When it comes to training details, both the text and image encoders are trained from scratch, since there is limited risk of overfitting due to the large scale of the web image text dataset. Rather than using non-linear projections popularized by SimClear, linear projections are used between the unimodal representations and the shared embedding space, since preliminary experiments revealed that a non-linear projection brought no benefits. A simple data augmentation scheme was used for the images, which involved random square cropping from resized images. Finally, the softmax temperature, tau, is learned during training to avoid setting it as an additional hyperparameter. In terms of models, 2 image encoders were considered. The first was a ResNet 50 backbone, incorporating some adjustments from later works to fix strides and anti-aliased pooling. The global average pooling layer is replaced with an attention pooling mechanism in the style of a transformer multi-headed query key value layer whose query is conditioned on the global average pooled feature. The second image encoder considered in this work is a vision transformer, largely following the original architecture, but with an additional layer norm before patch and position embeddings are fed to the transformer. For the text encoder, the authors explore various transformers trained on byte pair embedding text with a vocabulary size of 49,000. Each text description is capped to 76 tokens for efficient processing, then bracketed with start of sequence and end of sequence tokens. The embedding associated with the end of sequence token at the last transformer layer is used as the text representation. To assess the influence of increasing model capacity, the ResNet image encoder is scaled up by assigning equal compute budget to width, depth, and image resolution in the style of EfficientNet, while for the text encoder, the width of the model is scaled in proportion to the scaling of the ResNet. Let's look next at the nuts and bolts of the training process, beginning with model details. The authors train 5 ResNet image encoders, starting with ResNet 50 and ResNet 101, and then scaled versions of ResNet 50 by increasing compute by factors of 4, 16, and 64. Additionally, 3 vision transformers are trained, with patch sizes of 32, 16, and 14 pixels respectively. Finally, one further variant of the largest vision transformer is fine-tuned at a higher pixel resolution of 336 pixels for one additional epoch in the style of FixRes, which aims to address object scale discrepancies during training and testing that result from data augmentation during training. Each of these image encoders is paired with a corresponding text encoder of various widths and heads, with all text transformers using a 12-layer architecture. The authors found that the FixRes model works best, so this is used for most of their experiments. For optimization, the models were trained for 32 epochs using Adam with decoupled weight decay. The learnable temperature parameter was initialized to the equivalent of 0.07 used by Wu et al. In their self-supervised contrastive training method, with clipping employed to prevent logits from being scaled by a factor of more than 100, after it was found that this helped stability during training. A large mini-batch size of 32,768 pairs of images and text was used together with mixed precision for computational efficiency. Gradient checkpointing was further used to help reduce overall memory consumption. With the above setup, the authors trained their largest ResNet, the ResNet 50x64 variant, in 18 days on 592 V100 GPUs. To train their largest vision transformer, it took 12 days on 256 V100 GPUs. We come next to the experiments. To evaluate the trained CLIP models, the authors conduct 3 types of experiments. The first type, which forms the primary focus of this work, explores the zero-shot transfer abilities of CLIP. Zero-shot learning in computer vision is a term that has typically been used to describe the task of generalizing to unseen object categories. However, in this work, the term is instead used to refer to generalization to unseen datasets, which can be thought of as a proxy for unseen tasks. The rationale behind this approach is that zero-shot transfer in this manner can be thought of as assessing the task learning ability of a model, since each dataset effectively evaluates performance on a given task on a specific data distribution. This approach is inspired by works that have explored task learning in NLP, such as the notable example of the Wikipedia article generation method of Liu et al., which, in the process of performing this task, learned to reliably transliterate names between languages. Here, for example, the name of the person of the generated article is transliterated by the model into Hindi as a side effect of its training. In principle, evaluating models on unseen datasets seems a good proxy for unseen tasks. However, the authors note that, while useful as a motivation, this metaphor of datasets as tasks is not always particularly clear-cut. In part, this is because many vision datasets were introduced as benchmarks for generic image classifiers, rather than specific tasks. While it's clear that SVHN measures the task of street number transcription on the distribution of Google Street View photos, it's less clear what the task of CFAR10 is, even if we know the distribution of images, which are sourced from tiny images. Acknowledging this ambiguity, zero-shot transfer, as defined in this way, nevertheless offers to probe something of the task learning ability of a model. Despite this, it has received limited attention in computer vision. One exception is the visual engrams approach of Li et al., which the CLIP authors compare to in their experiments. As a second assessment, the visual representations learned by CLIP are evaluated with linear probes. Linear probes are used rather than nonlinear probes to avoid the introduction of additional hyperparameters and minimize the computational cost of evaluating many combinations of models and datasets. As a third assessment, CLIP models are evaluated for robustness on a collection of 7 natural distribution shift datasets, studied originally by Tauri et al. Let's turn to the first set of experiments and see how CLIP is used for zero-shot transfer. For this, it's helpful to first visualize the contrastive pre-training process. In each mini-batch, we assume that we have access to a collection of text descriptions together with corresponding images. The descriptions are passed through a text encoder, which produces a text embedding for each of the end descriptions, and similarly, the images are mapped through the image encoder to produce a set of n image embeddings. Then, cosine similarities are computed between all pairs of text and image embeddings, and then passed to a loss that encourages matching pairs, i.e. those highlighted in blue here on the diagonal, to be as similar as possible, while encouraging off-diagonal terms, which correspond to images and text pairs that don't match, to be as dissimilar as possible. Once trained, we can turn to zero-shot transfer. We first create a dataset classifier from the text associated with each label in a dataset by taking each class label, inserting it into a template, and then processing the result with the text encoder to produce one text embedding for each class label. To perform zero-shot prediction, given a new image, in this case of a dog, we pass it through the image encoder to produce an image embedding, which is then compared against each of the text embeddings, and the text embedding for which the similarity was highest, which is highlighted here in blue, is returned as the prediction of the model. A few extra details here about how this classification is performed. We first compute cosine similarities between the image embedding and the text embeddings. Next, we scale those similarities by the learned temperature, tau. And finally, we pass the results into a softmax to normalize the scores into a probability distribution. You can see that, in effect, we have formed a logistic regression classifier over the dataset labels. One way to interpret the text encoder is as a hypernetwork that is generating the weights of a linear classifier by conditioning on the label texts. It's useful to note that the text features for each class are cached, so the cost of text feature extraction is amortized over the set of all predictions for a given dataset. With the setup in place, we can look at the initial experiments conducted on zero-shot transfer. The authors first compared CLIP against visual n-grams, which had previously explored the zero-shot transfer task, on 3 datasets: Yahoo, ImageNet, and Sun. On these datasets, visual n-grams achieved scores of 72.4, 11.5, and 23.0 respectively. By comparison, the best CLIP model achieved scores of 98.4, 76.2, and 58.5. It's worth noting here that these are not controlled experiments. CLIP is trained with an order of magnitude more data, with a model that requires 2 orders of magnitude more compute per prediction, and using 3 orders of magnitude more training compute, but it gives some sense of the substantial gains achieved by CLIP. One factor that becomes particularly important during zero-shot transfer is the format of the text labels associated with each image, which can present challenges. Some datasets, for example, only provide integer class ID labels without their text descriptions. These cannot be used to evaluate zero-shot transfer, at least not without some researcher heroics to manually determine the text names of each class. Another issue that can arise is polysemy, in which the sense of a given word is ambiguous without context. For example, in ImageNet, there are 2 classes with the name crane, but one refers to the type of bird, and one refers to the machine used in construction. Without context, a zero-shot transfer model cannot know which is which. An additional factor to consider is that images are rarely paired with single words during training, but instead tend to be part of a description. It was therefore found that using prompt templates by inserting the class name into a sentence like a photo of a label, where label is replaced with the class name, can be useful. In fact, on ImageNet, just using this prompt alone brought a gain of 1.3% accuracy over using raw labels for the text embeddings. It was also found that customized prompt templates were useful for fine-grained classification. For instance, on Oxford IIIT pets, a good prompt was a photo of a label, a type of pet, while on satellite imagery, a satellite photo of a label worked well. A related technique that was found to further boost performance was prompt ensembling. For instance, we can average predictions made with the prompt template, a photo of a big label and a photo of a small label. In practice, the ensembling is performed over the embeddings rather than the predicted probabilities to enable caching, which allows us to amortize the cost of this operation such that it effectively adds no overhead over single prompt usage. It was found that by ensembling over a collection of 80 different context prompts, ImageNet performance was improved by a further 3.5% over using a single prompt. To study these effects more systematically, the authors evaluated the influence of prompt engineering and prompt ensembling over 36 datasets. Here, the plot shows model compute in gigaflops on the x-axis and average score on the y-axis. They found that, compared to using contextless class names as studied previously and shown here in blue, prompt engineering and ensembling, shown here in green, brought a 5-point improvement, equivalent to a factor of 4 improvement in model efficiency. The takeaway here is that prompts are important for zero-shot transfer. To conduct a more detailed and fine-grained analysis of zero-shot performance, a suite of 27 datasets was used. These include the 12 datasets used by Kornblith et al. In their study of whether better ImageNet models generalize better to other datasets, and an additional collection of 15 datasets to further extend the analysis, including the German traffic signs benchmark, and others that are sourced from VTab, which are likely to overlap less heavily in task definition with ImageNet. Among these, 2 are video datasets, for which classification is performed using frames as input images. 2 other datasets were curated by the CLIP authors themselves: Country 211, which targets geolocalization and comprises photos across 211 countries, and Rendered SST2, which evaluates optical character recognition performance. To evaluate performance, zero-shot clip is compared to a baseline consisting of a fully supervised linear probe on ResNet 50 features extracted from a model trained on ImageNet. This comparison is conducted on all 27 datasets. Here, the x-axis indicates difference in percentage accuracy between zero-shot clip and the linear probe. Cases where clip does better are shown in green bars to the right, and cases where the probe is better are shown in blue bars to the left. Examining the results more closely, we see that on fine-grained datasets, there are cases where clip does very well, such as Stanford Cars and Food 101, but there are also cases where it is weaker, such as FGVC Aircraft and Flowers 102. The authors suspect that this result stems from different levels of per-task supervision arising in the WIT and ImageNet datasets used for training. On datasets for general object category classification, such as CIFAR 10, CIFAR 100, STL 10, ImageNet, and Pascal VOC 2007, we observe fairly similar performance, consistently slightly in favour of clip. Interestingly, the result on STL 10 represented a new state of the art. For action recognition on video datasets like Kinetics 700 and UCF 101, clip strongly outperforms the baseline, possibly due to the fact that natural language may provide supervision for concepts involving verbs rather than the nouns that form the central focus of ImageNet. Finally, turning to datasets containing complex or abstract tasks like satellite image classification, lymph node tumor detection, object counting, German traffic sign recognition, and recognizing the distance to the nearest car, clip significantly underperforms the baseline. A takeaway here is that there is room for improvement to match non-expert humans on complex tasks. However, the authors caution that few-shot transfer, rather than zero-shot transfer, may be more meaningful for tasks where the learner has no experience, such as lymph node tumor classification, where humans without expertise would similarly be lost. One final comment on this chart. On the hallowed MNIST, or as Jeff Hinton sometimes refers to it, the Drosophila of machine learning, zero-shot clip struggles. Rather than comparing to fully supervised linear probes, we can also compare zero-shot clip with few-shot linear probes on various features from state-of-the-art supervised and self-supervised models, including clip itself. This comparison is conducted on the 20 datasets containing at least 16 examples per class. Here we see the results, with number of labeled training examples per class on the x-axis and average score on the y-axis. A first observation here is that zero-shot clip is much better than one-shot clip, and is closer to something like four-shot clip, which may appear odd. The authors note that this likely stems from the fact that zero-shot classifier can use the text class description to directly communicate the visual concept desired, whereas one-shot clip must infer the concept from training examples, which could be ambiguous in conveying the concept of a class. Some techniques were explored for combining zero-shot and one-shot clip to boost performance, but it was found to be non-trivial. Since the clip paper was released, there have been a number of follow-up proposals for how this can be achieved. One example is the tip adapter of Zhang et al. Overall, we observed from this experiment that zero-shot clip provides compelling performance, equivalent to the 16-shot performance of the strongest baseline included in this study, which was the ImageNet 21K BITM model. We can also perform an individual dataset analysis with the goal of estimating the data efficiency of zero-shot clip across datasets. For this study, rather than computing few-shot performance on every dataset with every possible number of shots, the authors evaluate 1-shot, 2-shot, 4-shot, 8-shot, 16-shot and fully supervised performance, and then estimate other values via log linear interpolation. The results are visualized here, with the x-axis indicating the number of labeled training examples per class to match zero-shot performance. At one extreme, we observe that there are two datasets, satellite imagery and flower classification, where zero-shot clip underperforms one-shot clip. At the other extreme, we observe that the top 20% of the datasets have a situation in which clip requires many shots to match zero-shot performance. This distribution is reflected in the fact that the mean number of shots across the benchmark required to match zero-shot performance is 20.8, but the median number is much lower at 5.4. As a point of reference, on ImageNet, clip requires 16 shots to match its zero-shot performance. We next compare zero-shot performance with a fully supervised linear classifier. This is useful because since the zero-shot classifier is also a linear classifier, we can use the fully supervised performance as an approximate upper bound on what can be achieved with zero-shot transfer. This is approximate in the sense that the fully supervised linear classifier may not be optimal, but is hopefully fairly close to it, given that it has access to the full training set for parameter estimation. The comparison is plotted here, with linear probe clip performance on the x-axis and zero-shot clip performance on the y-axis. The dashed sloped line in the middle indicates an optimal zero-shot classifier that matches fully supervised performance. In most cases, we observe that there is significant room for improvement in the zero-shot classifiers. There are, however, 5 datasets in which zero-shot performance is close to fully supervised performance. In this case, the absolute performance is also very high, leading the authors to suggest that zero-shot transfer may be most effective in cases when the underlying representations are of high quality. We also observe a relatively clear correlation between zero-shot performance and fully supervised performance. Next, we look at model scaling, which is of interest since several empirical studies have shown that deep learning system performance can sometimes scale smoothly with model capacity, dataset size, training compute, and other relevant quantities. In this study, clip performance is compared across a factor of 44 increase in model compute. Here, model gigaflops are plotted on the x-axis on a log scale, and average error is plotted on the y-axis. While individual evaluations are noisy, the overall trend is smooth and displays a similar kind of log linear trend to those seen in prior work. The second major group of experiments in this paper evaluate the representations learned by clip with linear probes. The authors first compare the average linear probe performance of clip on features across the 12 datasets studied by Kornblith et al. The x-axis denotes gigaflops per image for a forward pass, and the y-axis denotes average score. Here, the clip models are coloured red, with filled-in stars indicating clip vision transformer models, and empty stars indicating clip resnets. The small dotted lines on the right side of the chart indicate models that have been fine-tuned or evaluated at higher resolutions than was used during pre-training. The first observation we can make is that clip models scale very well with compute. You can see this from the steepness of the red curves for both the ResNet and Vision Transformer models. A second observation is that clip VITs are approximately 3 times as compute efficient as clip ResNets, a similar finding to the experiments of Dosovitsky et al., who also found that, given enough training data, vision transformers are more compute efficient than ResNets. The best overall model is a VITL-14, fine-tuned at 336 pixels for an additional epoch. In addition to the comparison over 12 datasets, linear probes are also evaluated over the more extensive collection of 27 datasets employed in the zero-shot experiments. Here we see a clearer separation between CLIP and other methods. On this broader suite, which has slightly less overlap with ImageNet in terms of task definition, the performance of self-supervised methods relative to supervised models also appears to improve slightly, with SimClav-V2 closing much of the gap to BITM. For a more fine-grained analysis, the authors next compare CLIP to the best performing baseline on the 27 dataset suite, Noisy Student EfficientNet L2. This plot shows the performance across each dataset, with the x-axis indicating change in score between the two models, and with green bars to the right indicating better CLIP performance, and blue bars to the left indicating better EfficientNet performance. For datasets that involve OCR, geolocalization, and action recognition, CLIP shows a clear advantage. This is also true for datasets relating to automotive themes, which the authors note may be a consequence of the narrow supervision provided by ImageNet, which has, for example, a single label for all traffic and street signs. CLIP underperforms EfficientNet on low-resolution images, which may be a consequence of the simple data augmentation employed during training, and perhaps unsurprisingly, on ImageNet, the dataset on which EfficientNet was trained. In a related vein, further analysis conducted by the authors show that each of the models trained on ImageNet are somewhat overfit to this task, while CLIP features are more robust to task shift, in that they generalize better to other tasks. In the third set of experiments conducted in this work, the authors evaluate the robustness of CLIP to natural distribution shift. The motivation for this analysis is that, since 2015, deep learning models have surpassed human performance, or at least human performance as courageously estimated by Andrej Karpathy. However, despite this, later studies have shown that these models still make simple mistakes and consistently fall below human performance on other benchmarks, suggesting a lack of robustness. The common explanation given for this lack of robustness is that deep learning is very good at learning correlations from training data, both useful and spurious, and it is the spurious correlations that fail to generalize, leading to a lack of robustness. However, most robustness studies to date have examined models trained on ImageNet. This makes it unclear to what extent robustness failures are due to ImageNet training, due to deep learning, or due to some combination of the two. Since CLIP models are trained with natural language supervision on a very large dataset that differs from ImageNet, and exhibit good zero-shot performance, they enable a fresh analysis of this question. In more detail, an analysis is conducted on 7 datasets, representing natural distribution shifts investigated by Taori et al. These datasets include ImageNet V2, ImageNet Vid, ImageNet Sketch, YouTube BB, ObjectNet, Adversarial ImageNet, and ImageNet Rendition. Collectively, these are datasets on which strong ImageNet classifiers tend to struggle to generalize. For instance, a ResNet 101 makes 5 times as many errors on these datasets compared to the ImageNet validation set. An analysis of CLIP robustness across these shifts is shown here, where on the x-axis we have average top 1 accuracy on class subsampled ImageNet, and on the y-axis we have average top 1 accuracy across the 7 datasets. The dashed line indicates an ideal robust model. Comparing to prior models trained on ImageNet, highlighted in blue, and existing robustness techniques, shown as grey dots, the family of CLIP, ResNet, and VIT models, shown here in purple, are quite significantly more robust. To get a sense of what these natural distribution shifts look like, and how they individually affect performance, the authors provide a visualization of samples from the banana class, which is common to 5 of the distribution shift datasets. We start with examples from the ImageNet validation set, on which an ImageNet trained ResNet 101 and zero-shot clip with the best VIT model achieve identical performance. Moving to ImageNet v2, which is a dataset collected from scratch that aims to follow the collection protocol employed by ImageNet, we see both models lose accuracy, but zero-shot clip loses less accuracy. On ImageNet renditions, the gap is far more striking. Zero-shot clip improves, while ImageNet ResNet 101 suffers badly. Large performance gaps can also be seen on ObjectNet and ImageNet Sketch, and most strikingly on the collection of ImageNet natural adversarial examples, where the performance margin is particularly dramatic. It is important to note that the strong zero-shot robustness of clip does not necessarily imply that ImageNet training causes the robustness gap. This is because of other elements of clip, such as its large and diverse pre-training, or its use of natural language supervision, which could produce robust models regardless of whether it was evaluated zero-shot or fine-tuned. To try to dig a little deeper into these factors, the authors conduct an experiment in which they first fit a logistic regression classifier to clip features on the full ImageNet training set. This plot shows the result of the experiment. As before, the x-axis indicates average top 1 class accuracy on subsampled ImageNet, while the y-axis denotes average top 1 accuracy across the 7 natural distribution shift datasets. Again, the dashed line indicates an ideal robust model with no loss of performance on the distribution shift datasets. The orange dots represent the various clip models evaluated zero-shot, and this dot in particular at the top denotes the best performing clip model. By adapting this model to ImageNet with logistic regression, we see a significant gain in ImageNet performance, as evidenced by a jump of about 9% to the right. However, rather than point upwards, the arrow points slightly down, indicating that the performance has actually gotten worse on the 7 natural distribution shift datasets. The authors note that it is somewhat surprising that such a major gain on ImageNet, corresponding to about 3 years of improvement in the state of the art, corresponds to no gain at all under distribution shift. Similar trends can be seen across the whole family of clip models. We can decompose this average performance change into the 7 natural distribution shift datasets for the best clip model together with ImageNet itself. The x-axis here indicates change from the zero-shot ImageNet classifier accuracy. At the top, we show that the 9.2% gain on ImageNet that follows from adaptation. The only other dataset to see a noticeable improvement is ImageNet v2, which was purposefully collected with the aim of replicating the ImageNet distribution. For other datasets, performance differences are negligible or markedly negative. One improvement to robustness enabled by natural language-based classifiers is that they can bridge differences in class schemes. For datasets like YouTube BB and ImageNet Fed, the classes are superclasses of ImageNet, requiring subclass predictions to be pooled. But with CLIP, classifiers can be generated based on the actual class name, avoiding the need for pooling. This adaptation to class shift brings a healthy gain in robustness, which is concentrated in datasets like YouTube BB and ImageNet Fid, for which there is a larger class shift. These analyses suggest that the zero-shot robustness of CLIP is lost after fully supervised logistic regression on the ImageNet training set. It's therefore interesting to consider how robustness varies for different few-shot values, here depicted in red, relative to the strongest zero-shot model, highlighted by the purple dot. The The broader trend here is that with fewer shots, CLIP moves slightly further ahead of the robustness of standard fully supervised models, but is still less robust than zero shot. More broadly, the authors suggest that a takeaway of their studies is that large-scale task and dataset agnostic pre-training coupled with zero-shot and few-shot evaluation on diverse benchmarks, as suggested by recent works, will likely lead to the promotion of robust systems and provide a more accurate evaluation of their real-world abilities. To see how CLIP predictions compare to those of humans, human predictions were gathered on the Oxford IIT PETS dataset, which is a 37-way dog and cat breed classification task. Humans were evaluated in zero-shot, one-shot, and two-shot settings. Here are the results. The columns with the term guesses in the title exclude predictions for which humans say, "I don't know," as their answer. A first observation is that humans get a major gain going from zero shot to one shot, but minimal further gain going from one shot to two shot. Interestingly, the gain from zero shot to one shot is almost entirely based on images that humans were uncertain about, indicating that they have a sense of what they don't know. The large gap from zero shot to one shot for humans suggests that there are likely improvements still to be found for machine sample efficiency, which does not yet exhibit this trait. Based on this, the authors suggest that integrating prior knowledge into few-shot learning may be a promising future direction. To characterize the errors being made, this plot, with accuracy on the y-axis, shows zero-shot CLIP performance in blue, as well as one-shot human performance in orange and zero-shot human performance in green, with the categories ranked by prediction accuracy for CLIP. Broadly, we observe that problems that are hard for CLIP are also hard for humans. The authors speculate that this finding stems from at least two factors. First, noise in the dataset, including mislabeled images. And second, out-of-distribution images which are hard for both humans and models. In addition to its use for classification, CLIP also has a number of immediate downstream applications, a few of which are explored by the authors. One application is retrieval, in particular the tasks of image retrieval, in which a goal is to rank a pool of images according to how well they fit a given query, and text retrieval, in which the goal is to rank captions according to how well they describe an image. CLIP is evaluated on two standard datasets, Flickr 30K and MS Coco captions. The results show that CLIP achieves equal or better zero-shot retrieval than prior work. CLIP is a little behind the state-of-the-art retrieval methods fine-tuned on the MS Coco dataset, but overall solid. The authors noticed early on in their project that CLIP appeared to be capable of some forms of optical character recognition. To assess this ability, they measured performance on 5 tasks requiring either direct or indirect use of OCR. To assess low-level character and word recognition, they evaluated on MNIST, SVHN, and IIIT5K, while for semantic tasks that require some use of OCR, they evaluated on hateful memes and SST2. They found that results were strongly dependent on the domain of the images. CLIP works better on rendered text than naturally occurring text, and also on the type of the text. CLIP appears better suited to words than numbers. Broadly speaking, CLIP achieved good results on the semantic tasks of hateful memes and SST2, okay results on IIIT5K, and poor results on MNIST and SVHN. For SVHN in particular, the authors note after some inspection that CLIP appears to struggle with repeated characters, as well as on the low resolution and blurry images found within this dataset. Next, given that CLIP has been exposed to a wide range of concepts, it is interesting to assess its ability to perform action recognition. This is done with both linear probe and zero-shot evaluations. For the linear probe experiments, The middle frame of each video is used to compute features, rather than all frames to reduce cost. For zero-shot evaluation, which is much cheaper, all frames are used. Experiments are conducted on UCF 101, Kinetic 700, and Rare Act. The results indicate encouraging linear probe and zero-shot performance on UCF 101 and Kinetic 700, suggesting that CLIP has indeed learned something of actions. On the Rare Act dataset, comprising unusual actions like drilling an egg, CLIP improves strongly over the existing state-of-the-art. Finally, it was noted during development that CLIP seemed to be capable of recognizing many different locations. The authors quantified this on two tasks: on the new country 211 data that was collected as part of this work, and for which results were included in the 27 dataset suite discussed earlier, and on Im2GPS, which requires models to regress the GPS coordinates of images. To perform the latter task, GPS coordinates were estimated via nearest neighbours against a set of 1 million reference images that were compared via CLIP embeddings. This approach achieved solid results on Im2GPS, suggesting that CLIP does indeed have some knowledge of location. Let's look next at data overlap analysis. One important issue for studies involving large-scale internet dataset pre-training is the potential for unintentional overlap between the training set and downstream evaluation datasets, potentially invalidating generalization results. One solution to this issue is to remove all duplicates between the training set and the test set before training a model. This has the advantage of guaranteeing true downstream held-out performance, but also has the major disadvantage of requiring the researcher to know all possible test data ahead of training, potentially limiting the analysis that can be performed on the model. An alternative approach, and the one taken in this work, is to carefully document how much overlap occurs between the training set and each evaluation set, and how much the evaluation performance is changed as a result of these changes. To implement this strategy, for each evaluation dataset, a three-stage pipeline is used. First, to estimate contamination, a new duplicate detector is run on the evaluation set. Then, manual inspection is used to set a threshold for this evaluation dataset that achieves high precision and recall examples near duplicates in the training set. The evaluation set is then split into two subsets: clean images that fall below this threshold and overlapping images which lie above the threshold. And finally, we use the name all to denote the set of all images. We then report the data contamination for the dataset as the ratio of the number of images in the overlap subset to those in the all partition. Second, to estimate the performance change due to contamination, the zero-shot accuracy of a CLIP ResNet 50 x 64 model is computed on the overlap, clean, and all splits. The difference of the accuracy on the all split and the clean split is reported as a metric for performance change. Third, to assess significance, a binomial significance test is run using accuracy on the clean partition as the null hypothesis and computing a one-tailed p-value for the overlap subset. In addition, 99.5% Klopper-Pearson confidence intervals are computed on the overlap subset. When it came to implementing the near duplicate detector, the authors found that CLIP embeddings are not a good choice because they reflect semantic rather than low-level similarity. Instead, they train a ResNet 50 model with an info-NCE loss to discriminate augmented versions of images from other images within mini-batches. The training set used for this task was a subset of 30 million images taken from the full 400 million dataset. At the end of training, it was found to achieve nearly 100% accuracy on the proxy task of detecting augmented variants. Turning next to the results, we find that across the 35 evaluation datasets considered in this work, there is a median overlap of 2.2% and a mean overlap of 3.2% with the pre-training dataset. Among these 35 evaluation datasets, a total of 9 were found to have no detected overlap at all with the pre-training dataset. Of these 9, some contain specialized or synthetic data such as MNIST, Clever, and GTSRB, rendering them unlikely to be posted online as typical images, while others simply contain data that was created after the pre-training dataset. Examples include ImageNet and hateful memes. To visualize the overlap and its influence, this plot depicts an analysis across each dataset. The x-axis indicates the percentage of data overlap, while the y-axis indicates the difference in accuracy on the overlap and clean subsets of the data. So, moving left to right, we see datasets with increasing overlap, with one dataset, country 211, having an overlap of over 20%. This particular dataset is curated from YFC 100 million, which forms part of the mix of the 400 million pre-training images used by CLIP. However, possibly due to the fact that its task is geolocalization, and the fact that its training texts do not typically mention the location of the image, CLIP seems to attain no benefit from the overlap. Another observation here is that although several evaluation datasets have non-trivial overlap, only 5 have 99.5% Klopper-Pearson intervals that rule out a 0% difference in accuracy. Of these two datasets, Kinetic 700 and ImageNet Sketch have worse performance on their overlapping data than on their clean data, while the remaining 3 datasets benefit from the overlap. A further plot charts detected data overlap against the overall accuracy that is due to the overlap. Here, only 6 of the datasets exhibit a statistically significant improvement under a one-sided binomial test. The authors note some limitations to this analysis. The first is that the near-duplicate detector is imperfect. Although it performed well on its proxy task, it is simply infeasible to manually validate its performance across 400 million images. The second limitation is that there may be subtle distribution shifts in the overlapping subset that form a nuisance factor in the analysis. For example, much of the overlapping subset of kinetics consists of black transition frames. This may explain why performance is harmed on the overlapping split. Taken together, a reasonable summary of this analysis is that data contamination does not appear to have a major effect on the results. This is a finding that mirrors the analysis conducted in previous large-scale pre-training works. We turn next to the limitations of CLIP identified by the authors. First, while zero-shot CLIP is competitive with a supervised linear probe on ResNet 50 features, it lags far behind the state-of-the-art on most datasets considered here. While scaling has improved accuracy so far and does not appear to be tailing off, approximately 1,000 times more compute would be required to reach overall state-of-the-art performance, which is not feasible on current hardware. Thus, further research is required to improve the efficiency of CLIP. We saw earlier that CLIP struggles on abstract tasks like counting the objects in an image, on certain fine-grained tasks like differentiating species of flowers, and on tasks that fall outside the pre-training data. For data that is truly out of distribution, such as the digits of MNIST, CLIP achieves only 88% accuracy, which is strikingly low, underperforming logistic regression on raw pixels. In light of its good performance on other OCR evaluations, this strongly suggests that CLIP does not address the brittle generalization associated with deep learning, and instead, it rather hopes that all test data is effectively in distribution by virtue of its vast and diverse pre-training dataset. However, as the MNIST results demonstrate, this assumption is easily violated in practice. A second limitation of CLIP relates to its flexibility. It is limited to choosing among concepts in a given zero-shot classifier. In this sense, it is less flexible than image captioning, which was also explored in preliminary experiments for this work, but rejected due to its low data efficiency. Future work could potentially address this by combining the efficiency of CLIP with the flexibility of image captioning. A third limitation relates to the fact that CLIP inherits the poor data efficiency of deep learning. It aims to compensate for this by using a scalable pre-training source that can be grown to hundreds of millions of examples. A fun fact is that if each image seen by CLIP was shown at 1 frame per second, it would take 405 years to iterate through the full 32 epochs of training, which corresponds to 12.8 billion images. In terms of methodology limitations, despite the focus on zero-shot learning, repeated querying of validation sets was used to guide CLIP development. Additionally, the authors note that while experiments were reported on the 12 datasets used by Kornblith et al. To minimize selection bias, the broader suite of 27 datasets on which CLIP provides the most compelling results is somewhat heuristically assembled and co-adapted with the development and capabilities of CLIP. A new benchmark of tasks that aim to assess broad zero-shot transferability rather than reusing existing datasets could help avoid this. CLIP is trained on uncurated internet image and text data, and as a consequence, it learns the social biases present in this data. Finally, there is clear room for few-shot performance improvement, given that it often falls below CLIP's zero-shot performance. This is notably different to the gains obtained by humans in the one-shot setting, so further research on this topic is needed. Next, we will discuss the broader impacts of the work identified by the authors. The authors consider several aspects of CLIP with regard to its broader impact. First, thanks to its promising zero-shot performance, CLIP has a broad range of applications. Since it allows its user to create classes for categorization, i.e. to roll their own classifier, it is particularly challenging to characterize CLIP, because capabilities of the model may become clear only after testing for them. In terms of direct applications, it's clear that CLIP shows significant promise for tasks like retrieval, and also possibly for novel applications enabled by its limited need for specialized task data. To try to characterize the behavior of the model, the authors conduct analysis studies that look at CLIP performance on the Fairface benchmark, investigate bias probes, and explore its performance for surveillance, since this is an application with particular societal implications. They note that these bias tests are naturally limited in scope, with further analysis required for any given deployment of the model. One additional note here is that it has been observed that algorithm design, training data, and class definitions, or taxonomies, or class design, as they term it here, have implications for social biases. This latter aspect of class design is particularly important for CLIP, since anyone can define their own class. To begin their analysis, the authors conduct experiments on Fairface, a dataset of 106,000 images that are approximately balanced across 7 race categories, with images that have been annotated with estimated age, race, and gender. On this dataset, they find that CLIP features with a linear probe mostly outperforms existing baselines on race, gender, and age classification, with zero-shot CLIP achieving more mixed results. On the specific task of gender classification, both the linear probe and zero-shot CLIP models achieve an accuracy above 95% for all races, with relatively limited differences across races. While this may be encouraging, the authors note that such probes offer only one approximation of the algorithmic fairness, which is a complex issue. Continuing on the analysis on Fairface, the authors next employed zero-shot CLIP to classify 10,000 face images, where this time the Fairface classes had been augmented with non-human labels like animal, gorilla, chimpanzee, and orangutan, as well as crime-related labels like thief, criminal, and suspicious person. The question under focus here is whether these terms are disproportionately assigned to particular demographic subgroups. The first experiment looked at the percentage of images classified into crime and non-human categories. Faces annotated as white and Indian saw the greatest number of assignments to crime-related categories, while faces annotated as black saw the greatest number of assignments to non-human categories. A further analysis looked at how the images misclassified by CLIP are broken down by age. With the default label set, the youngest age groups have the highest number of misclassifications. However, by appending the child class label to the set, these errors are substantially reduced. A takeaway from this study is that class design can play an important role when investigating model misclassifications. The authors next conducted a study to analyze CLIP's prediction across genders on US Congress. To this end, they first constructed some new label sets, one comprising 300 occupations, the second comprising labels predicted across Congress photos by cloud vision services. As a first experiment, CLIP was employed for gender classification, on which it scored 100% accuracy. Next, CLIP's labels assignments across genders at a 4% probability threshold were analysed, with the most common occupations being lawmaker, legislator, and congressman assigned by the model. The authors note that biases for models like CLIP may be revealed at noisier, lower thresholds, and indeed, at a 0.5% threshold, they found that nanny and housekeeper start appearing as labels for photos of women, while prisoner and mobster start appearing as labels for photos of men. A further analysis was conducted by exploring the distribution of labels assigned by CLIP at a 0.5% threshold across the label set predicted by cloud vision services. At this threshold, labels relating to appearance, particularly for hair, are commonly assigned to women, while other appearance labels such as suit, tie, and necktie commonly appear for men. One takeaway observation from these studies is that the findings are heavily influenced by the choice of probability threshold, in addition to the choice of labels. In this case, for example, certain occupational associations for genders only showed up at the lower probability threshold. The next application considered by the authors was surveillance, for which they sought to measure zero-shot classification on footage from CCTV cameras obtained from the Virat dataset and other sources. CLIP is then tasked with predicting coarse-grained and fine-grained labels for the images. The coarse-grained labels capture the main subject of the image, such as empty parking lot or school campus, while fine-grained labels capture smaller features among the video frames, such as the person standing in the corner. It was found that coarse-grained accuracy across label sets containing at least 6 labels per image, and also including hard negatives with some similarity to the ground truth label, was 51.1%. Fine-grained accuracy was near random. A simple takeaway from these experiments is that CLIP is not outstanding at zero-shot classification on CCTV surveillance footage. A second experiment considered the problem of zero-shot celebrity recognition on 8,000 Celeb A images. Results are shown across 4 CLIP models here, with the best model obtaining 59.2, 43.3, and 42.2 top 1 accuracy over 100, 1,000, and 2,000 classes respectively. While these results are far from state-of-the-art for modern face recognition systems, they are notable since the recognition was performed solely from the pre-training data, where CLIP must have learned these celebrity names. With this in mind, the results are quite striking. Summarizing these experiments, the authors note that, given existing high-performance specialized surveillance systems, the appeal to use CLIP for such tasks may be relatively low. However, by removing the need for training data, CLIP could enable bespoke surveillance systems for which there are no existing models or training data readily available. Relatedly, it could also lower the skill required to build such applications. Next, we turn to related work. The CLIP paper describes a large number of works that formed the inspiration for its approach. Here I will briefly summarize a few of these salient papers. One of the early approaches for focusing on image retrieval with text was introduced by Mori et al. With a method they termed image-to-word transformation.
This was effectively a captioning method that enabled the construction of a text keyword index for images. In its initial learning phase, it took as input a collection of images with corresponding descriptive words. Each image was then divided into parts, with each part inheriting the words from the full image description. A feature extraction step coupled with vector quantization was then used to perform clustering, with the frequencies of words of all partial images accumulated in aggregate. From this clustering, conditional probabilities are estimated for every word via their frequencies. During inference, the system takes in an image without text, divides it into parts and extracts features, and then finds the corresponding nearest centroids in the feature space for each part. The conditional probabilities are then accumulated across assigned centroids, and the words with highest likelihood are assigned as the description. A second important aspect of CLIP is its use of large-scale image-text data sourced from the web using search engines for scalability. An example of an early work by Fergus et al. Exploring what has later come to be known as Webley supervised learning demonstrated the utility of scaling up training data with search engines. Their framework consisted of entering keywords for target categories of interest into Google image search, collecting the results, and using them to train a category model. Each test image was then classified using the model learned on the search results. One previous work illustrating the value of large-scale vision and language pre-training was introduced by Miech et al., who gathered a dataset of 136 million video clips from how-to tutorials on YouTube. They then showed that these clips could be used to pre-train a joint embedding for text-video retrieval and action localization. They also showed that this embedding transferred well to content domains beyond instructional videos, highlighting the benefits of scale. Finally, there have been many works designing systems that jointly model vision and language with forms of cross-attention. An example is the Vilbert model of Liu et al., which ingests vision and language tokens and processes them in parallel streams with co-attention layers. The model is trained in a BERT-style manner, with a mask prediction loss and a loss on predicting whether the vision and text correspond. Note that Vilbert differs from the CLIP architecture. In CLIP, the only cross-modal interaction happens at the end of the network. One additional difference between CLIP and these latter two recent works is that CLIP trains its visual encoder completely from scratch, rather than building on pre-trained classifiers or object detectors. Finally, we conclude with a brief summary. This work has investigated the feasibility of replicating the NLP success of task-agnostic web-scale pre-training in the field of computer vision. Through a range of experiments, the authors have shown that computer vision also benefits from such an approach. During pre-training, it appears that CLIP learns to perform a wide range of tasks. Most intriguingly, this pre-training enables CLIP to perform zero-shot transfer to many datasets, opening up a host of further applications and interesting research questions. That's it. We've reached the end. Thank you for your attention.